Okay, so today too, um, we want to know how we can transform a Laplace of t exponent n. Okay, so Laplace transformation, and we've already learned from our previous videos that this is the basic definition for Laplace transform. Okay, so just write integral from 0 to infinity e exponent minus st, multiplying the function that will be given inside the Laplace. That's the f of t. But here, the f of t, or the function within the Laplace, is t exponent n. So you repeat that function there. Then you multiply it by dt. So basically, that's what we have been doing. Okay. So after writing it in this form, then we ask ourselves, how can we integrate e exponent minus st multiplying t exponent n? So this is an exponential function. This to some function t exponent n. So we have to use integration by parts. Okay. So basically that's what I've written here. So I've not changed anything. Okay. It's here. Okay. So we take the limit as h or some variable. Okay, so h is a constant. Sorry, is a variable. It could be a, it could be b, it could be c, it could be anything. It's a constant. So we just take that new that alphabet. So here I always use h. So limit as h approaches infinity of integral from 0 to infinity of e exponent minus st t exponent n multiplying the t. Okay, so as I said, this is integration by parts. Okay, so you just make a substitution for your u and t exponent, for your u to be t exponent n. Then you make your div to be e exponent minus st. So this is your div e exponent minus st dt, and this t exponent n, that's your u. Okay, so when you differentiate u with respect to n, you are going to get, you see, the n will come and multiply the differential of t exponent n. Okay, so n will come and multiply the t exponent n, then you subtract 1 from it, so we are going to get n t exponent n minus 1. That's how the derivative, that's the general rule for a derivative. Okay, so this place to, when we integrate the v, you are going to get v, and also when we integrate e exponent minus st with respect to t, we are going to repeat the exponential part, that's the e exponent minus st, then we differentiate the exponent part, that's the minus st with respect to t, and when you do that, you are going to get s, because with respect to t, the t will yield 1, then 1 times s, you are going to get s, but you divide the result. Okay, so you are going to get minus 1 over s e exponent minus st. Okay, so so this is the substitution we use to make u v minus integral of v du. That's the integration by parts substitution we used to make. Okay, so after getting your u to be this, your v to be minus s over e exponent minus t, your du to be n times t exponent n minus 1, just make a substitution here. So that's what I have done here. Okay, so you are going to get the u was t exponent n times the v to, we had minus 1 over s e exponent minus st, then we apply the limit as from 0 to infinity. So that infinity, I chose a constant or a certain variable h. Okay, then minus, so this is the minus of the integral. Okay, I'm just making a substitution. So minus the integral to from 0 to the a certain limit h of the v du. I know that the v, I had minus 1 over se exponent minus st. This is the v. minus 1 over s e exponent minus st. Okay, then multiplying t exponent n. So the t exponent n is the u. That's uh, multiply n times t exponent n minus 1. That's the du. Okay, so I'm going to get, sorry, this place is n. Okay, so we are going to get n times t exponent. Okay, so you are going to get n times t exponent n minus 1. Okay, sorry, so minus 1. Minus 1 was here, minus 1. Okay, so n minus 1 dt. Okay, so then after that, we just make a substitution for the limit. Okay, so we just take this part. So t exponent n multiplying minus 1 over s e exponent minus st, just factorize the constant out. So you are going to get t exponent n over s negative, remaining e exponent minus st. Then we take the limit from 0 to h. So h is the infinity. So you should note h is the infinity. Then the negative 2 will come out. Then multiply the negative here. So you are going to get positive 1 over s as is from 0 to h e exponent minus st nt. This is the nt n exponent 1. Sorry, n exponent t exponent n minus 1 dt. Okay, so as h approaches infinity, I'm going to make a substitution. So the substitution that we make a substitution for t, not s. So always keep that in mind. Okay, so whenever I see t, I will just introduce the h. Then that h approaches infinity. So I will just substitute in infinity there. So I'm going to get minus infinity exponent n over s. This is this. Okay, multiplying e exponent minus infinity because the t here is the h. So that's the where we are making the substitution. Okay, then we know that is the upper limit minus the lower limit. So minus the lower limit. So I'll plug in the lower limit 2. So the lower limit 2 is 0. And whenever I see t, I'll just make a substitution of 0. So I will get 0 exponent n. So 0 exponent n. Okay, over s. Okay, so 0 exponent n over s. So this is 0 exponent n over s. Multiplying e exponent 0. So e exponent 0. That's the t, which is 0. E exponent 0 is 1. But since 0 over s or 0 over any number is 0, the whole of this equation will turn to 0. And the whole of this equation too, we know that e exponent minus infinity is 1 over infinity. Okay, e exponent minus infinity is 1 over infinity. And 1 over infinity is 0. 1 over infinity is 0. So the whole of this place will be 0 multiplying the whole of this place. So the whole of this place will yield 0. Okay, so we are going to left with the only these parts. That's so the n, I can pull my n here out. So I'm going to get n over s because n over s. Then the remaining ones, that's e exponent minus st, t exponent n minus 1 dt. Okay, so I'm left with this. Okay, so I'm left with this. So we can clearly see that t exponent n minus 1 2 is a Laplace. Okay, it's a Laplace. It's a certain function. Okay, so when I ask you, let or say write a Laplace for t exponent n minus 1, this t exponent n minus 1, you are just going to write the limit from 0 to infinity e exponent minus st and whatever the function. So basically that's the idea. This two is a Laplace transform of t exponent n minus 1. Okay, so we also integrate this one by parts. we also integrate this one by parts. Okay, so for what we did for the previous ones, you just make your u to be t exponent n minus 1, then you make your dividend to be e exponent minus st dt. Okay, so e exponent minus st dt. Okay, so you just differentiate u with respect to n, and the n minus 1 will come, then you subtract 1 from the exponent. That's what we intend to do for a derivative. Okay, so you are going to get this. Then yet we are going to get integral of the v, you are going to get v. Then when you integrate e exponent minus st, you are going to get, we are going to maintain the e exponent minus s, then you divide by whatever result we had. So when you differentiate minus s with respect to t, we are going to get s. So then you divide. Okay, that's how we had this. So just make a substitution again. So my substitution is uv minus integral of v du. That's for the integration by parts. Okay, so that's what I have done here. So my u is t exponent minus 1. So this is your t exponent minus 1. My v is minus 1 over s e exponent minus st is here. Then I take the limit from 0 approach from 0 to h minus the integral, so minus the integral of v du. So this was my v, that minus 1 over s e exponent minus t, and this was my du, n minus 1 t exponent n minus 2. Okay, so the same thing when I just make a substitution as h approaches infinity. So the minus 1 over s can come out of the equation here. So I'm going to get minus 1 over s coming out, leaving t exponent n minus 1 e exponent minus st. Okay, so just make a substitution for the t, not s. So whenever we see t, we place infinity there. So we are going to get infinity. So your infinity. Okay, so I'm going to get infinity exponent n minus 1 multiplying e exponent minus st to e exponent minus infinity. Okay, so e exponent minus infinity is 1 over infinity, and 1 over infinity is 0. So 0 is going to multiply the whole of this, so it makes the whole of this go to 0. Okay, then we also plug in, you know that it is the upper limit minus the lower limit. So after plugging in the infinity, we also consider the lower limit, which is the 0. We also make a substitution for the 0. So whenever we see t, we just place 0 there. So you're going to get 0 exponent n minus 1. Then you're going to get minus 1 over s e exponent 0. So e exponent 0 is actually 1, but because 0 exponent n minus 1, it makes the whole of this place 0. Okay, so we are remaining only this part minus integral of from 0 to h of minus 1 over s e exponent minus st multiply n minus 1 t exponent n minus 2. So we are only left with that part. The uv part is this, and this the minus v du. So we are left with this part. So what this basically means is that the minus will come out, so it becomes positive. So I'm going to get positive of this. But remember, it was n over s multiplying the whole of this. So if you've gotten the whole of this to be this, only remaining, because this all this approaches 0, and we only remain with this. So the n over s will multiply through this. So just factorize n minus 1 out. So that's what I've done here. So the n over s will multiply the whole of this. So the n minus 1 will come out and multiply, is a constant, so it will come and multiply n times n minus 1 all over. Then the s2 will multiply s, you are getting s squared. So integral from 0 to h e exponent minus s t exponent minus n minus 2 dt. So we are resulting this. Okay, so what this one also means is that we've also gotten another Laplace, because when we apply a Laplace of t exponent n minus 2, So the idea is that whenever we applied a Laplace when it was t exponent n, the n came out. The n came out. So this place, whenever we apply a Laplace of the t exponent n, the n came out over the s. So this tells us that whenever we also take a Laplace of t exponent n minus 1, t exponent n minus 1, so the same thing, we saw that the n minus 1 also came out and the s also came out and they multiplied and we had t n multiply n minus 1 over s squared. So here too, when we further do this, the n minus 2 will still come out. Then the s will still come out and multiply s squared. So we are going to get n times n minus 1 n minus 2 all over s cubed. If you can try this, you are going to get this. Okay, so me having this tells me something. We learned from our basic school or SHS that whenever we have something like this, n multiply n minus, we see the function is decreasing, okay, by some constant minus 1, minus 2. So we can write this as n factorial. Oh, okay. So then by comparing the s, initially it was s, then we came to s squared, and this one too also gave us s cubed. So I can derive an expression that, oh, okay, then s is s exponent n plus 1. Okay, so that's how we have a Laplace transform of t exponent n, then n is equal to n factorial over s exponent n plus 1. Okay, so thank you very much. These are some examples that we need to solve. So whenever we apply Laplace transform of t exponent, and you are going to get n factorial over s exponent n plus 1. So example, we should apply a Laplace transform for t exponent 3. So you are going to get the n here is your 3. So you are going to get 3 factorial over s exponent n, which is the 3 plus 1. So you are going to get 3 factorial is 3 times 2 times 1. Remember, 3 times 2 times 1. Okay. All over s exponent 3 plus 1, you're going to get 4. Okay. So you're going to get 6 over s exponent 4. So the same thing, when you have a Laplace of t exponent 2, you are going to get 2 factorial over s exponent n plus 1, which is 2 plus 1. Okay. So you're going to get 2 times 1 over s cubed. So this is the answer. Okay. Thank you very much.